Hello everyone. In this video, we'll learn how to use Oxide to model oxygen partial pressure control during oxidation of metals. In steel industries, the cold-worked metals are annealed at elevated temperature under the protective atmosphere of nitrogen and hydrogen gas mixtures. Although the annealing is carried out under the protective atmosphere, but sometimes moisture enters this annealing environment, and then this moisture dissociates into hydrogen and oxygen gases. Now, this oxygen gas fuels the oxidation of steel surfaces. These surface oxides are very detrimental to the zinc adhesion during hot dip galvanization process. The moisture content in the furnaces are indicated by its dew point temperature. So, the dew point temperature is a temperature at which the atmosphere gets saturated by its moisture content. Therefore, the higher and positive the dew point temperature is, more moisture content is there in the atmosphere. Also, the dew point temperature can indicate the partial pressure of oxygen in the atmosphere. So positive the dew point temperature, the partial pressure of oxygen will be much higher, and then the atmosphere can seriously oxidize the steel surface. Therefore, in Faxage, we'll try to calculate the partial pressure of oxygen if the atmosphere or the furnace, uh, it means the composition of the atmosphere is given, and also the dew point temperature is given. Then using Faxage, we'll calculate the partial pressure of oxygen. Now, for this calculation, we'll take the furnace atmosphere to have 95% nitrogen gas and 5% hydrogen gas. Also, we'll take the dew point temperature as minus 30 degrees centigrade, and the annealing temperature is 800 degrees centigrade. Now we'll use this information in Faxage. In Faxage software, in order to do the calculation, we have to open the Equilib module. To open the Equilib module, we have to go to the Equilib option and left mouse click on this option. After the Equilib module opens, we have to first select the database to do the calculations. In order to select the database, we have to first go to the data search option and left mouse click on it. In the data search, we will select only fact-based database because all our compounds are pure compounds and gases. Therefore, after selection, we will click on OK with left mouse click. After that, we have to enter the gas composition. So in our gas, we have nitrogen, hydrogen, and also we will introduce moisture. So in order to add the reactants, we have to go to this plus option, which is as it shows, add a new reactant, and then left mouse click on it. So these are added. Then we have to input the name of the chemical formula of the species. So we will enter nitrogen, we'll enter hydrogen and H2O. So as discussed before, our nitrogen is 95, hydrogen is 5, and we are entering the moisture as H2O. Then after entering the amount and the chemical formula of the species, we'll go to next to go to the menu window of Equilib module. Here we have to select all the compound species. So we'll select gases, pure liquids and solids, and also as we have very low temperature, sub-zero temperature, as the dew point is -30, we should select real gas to obtain accurate Gibbs free energy and volume fraction of the gas at this low temperature. So we select real gases and then we'll enter the dew point temperature, which is -30 degrees centigrade. After inputting all the information required to do the calculation, we will click on calculate with left mouse click button. So here, as we can see, we have the composition of the gas and the solid ice which is in equilibrium with it. So we'll take, so in order to do the calculations at our annealing temperature, we have to take this gas phase at 800 degrees centigrade, which is our annealing temperature. Therefore, we have to make a stream file. In order to make a stream file, we have to go to output option and left mouse click on here. Then we have to go to stream file and then here we have to go to save stream file. Now we want to save the gas phase. So save gas phase. Here we want to save this gas phase as gas at -30 degrees centigrade. You have to name the stream file name here and then after naming it we'll click on save with our left mouse click and then the comment is this is a gas, so we'll comment this as a gas, then OK. So our gas file is saved as a stream file. Next, we have to use this stream file which we created right now and we have to increase the temperature to our annealing temperature, and for this problem we have to go to 800 degrees centigrade. In order to do that, we have to return to our main window, which is reactants window, and then clear the information here. To clear this, you have to go to edit. So go to edit and left mouse click on it and then click on clear option. So you want to clear the current system, so click on yes with left mouse click button. Then we have to import the stream file which we just created. To do that, you have to go to edit options again and then click left mouse click button. Then we have to open the mixtures. So go to mixture and streams, import a stream, and here we have gas 30 degrees centigrade, the stream which we made before. We click on it. So this is gas mixture with dew point -30 degrees centigrade. Now we'll go to next. Here we'll select the gas which is a real gas and then pure solids, pure liquids and pure solids. Now we have to input the annealing temperature 800 degrees centigrade, and then we have put all the information required, so we have to go to calculate and then click left mouse click button. So FACSH calculates the gas composition, and here we can see we have oxygen which has partial pressure 2.398 into 10 to the minus 23. This is the partial pressure of oxygen, which corresponds to the dew point minus 30 degrees centigrade at 800 degrees centigrade. Now if we want to check that how the partial pressure of oxygen changes with different annealing temperature for a fixed gas composition and for a fixed dew point temperature, we have to go to the previous page and then input the range of temperature which we want to check, the range of annealing temperature. Here we'll put from 500 degrees centigrade to 1200 degrees centigrade with 10-degree interval, and then we want to calculate it. So we go to calculate and click left mouse click on it. As we see, for different temperatures it has given us gas composition, and there we have different partial pressures of oxygen. Now if we want to visualize it nicely, so we'll plot the partial pressure of oxygen in log scale with different temperatures in x-axis. To do that, we have to go to output and left mouse click on it, then go to plot, then click on plot results. Here in plot results window, first we have to select the axis and the species for which we want to check the results. So first we'll select the axis. To select the x and y axis, you have to go to axis and left mouse click on it. Here in the variables, in y variable, we'll plot the partial pressure, which is the activity of oxygen in our y-axis, and in x-axis we'll plot the temperature. So to put the y variable, you have to go to y variable and left click on it and select activity with in log scale, and then we select the x-axis. So the x variable will be temperature. So the temperature range will be 500 to 1200 degrees centigrade as we put before, and then we'll put the activity range. So here we'll put minus 35 to minus 15. That will be enough to see, and we'll take on every one interval. Then after we put all the information of our axis, we click on OK with left mouse click. So after this we have to select which gaseous phase activity you want to see. So we'll select oxygen from the gaseous species. So to select it, we have to go to this white region and left click on it. After selection, it will show plus sign, and then click on OK. After doing that, all our information regarding the plot is inputted, and then we'll click on plot. So here you can see that the log activity of the oxygen gas is plotted in the y-axis, and the temperature range is also plotted in the x-axis. So if you want to change the name, so you have to go in here and then left mouse click on it twice, and frame and access dialog box opens. Here we can change the name, the activity, to partial pressure of oxygen, and we click OK. So this is our required graph, which shows the relationship between partial pressure of oxygen and the annealing temperature. We can do this for several other dew points for a fixed gas composition. So first we have to save this figure in order to superimpose for other dew point temperatures. So to do that, you have to go to File, click on it, and click on Save As. This window pops up, and we can give the destination of this file to save. I'm selecting on desktop, and I'll give the name gas at -30 centigrade. Similarly, we can do this calculation for different dew point temperatures. Now, if we want to calculate for other dew point temperatures, the same process, you can make other diagrams in the same way I showed before, and to check the relationship of partial pressure of oxygen at different temperatures with different dew points, we have to make similar diagrams at different dew point temperatures by making stream files, and then we have to superimpose the data. So this data is for -30 dew point, so I will just first change the name of the axis, and then mark this as dew point -30. To do that, click on the line and then go to this add label option and left click on it, and then type -30 degree centigrade. Similarly, I have calculated for other temperatures, and I'll superimpose those diagrams. In order to superimpose, you have to go to the superimposed figure option and left click on it. So I have all the diagrams in my desktop, so I'll just superimpose one after another. So this is for -20 degrees centigrade. I'll level it, Similarly, I'll superimpose all the other lines and show it. So after superimposing, this is the final data. So it shows the partial pressure of oxygen in y-axis, the temperature in the x-axis, and the variation for different dew point temperature for a fixed gas composition of 95% in nitrogen and 5% hydrogen. Similarly, we can draw this kind of diagram for different gas composition and check how for different handling temperature our partial pressure of oxygen is calculated at different dew point temperatures. In the next problem, we want to draw oxidation diagrams of iron, 1% manganese and 1% silicon alloys. So in this case, the alloy composition is fixed. So we want to check that for different partial pressure of oxygen and with different temperatures, what type of oxide phases forms for a fixed composition of metal. In order to do that, we first open FactSage. In FactSage, we open phase diagram. We just want to plot a phase diagram. So to open phase diagram, we have to go to this phase diagram option and left mouse click on this option. Here is this phase diagram dialog box opens, and in this module, we first to select the databases which is required for this calculation. To do that, we have to go to this data search and left mouse click on it, and we'll have oxygen as gaseous phase, so we'll take FACTPS. We'll have oxide phases, so we'll take FT oxide, and then we have steel composition as I showed before, so we'll take FS steel database. So after taking all the required databases, we'll click on OK with left mouse button. Now we have in our components, we have to add our alloying element components. So to add new reactant, we have to go to this plus sign and click with left mouse click. In our alloy, we have iron, we have manganese, we have silicon, and we have oxygen. After putting all the components, we have to go to next. Here we have to select all the possible product phases. So first we'll take all the pure solids, and then we'll take all the solutions. To select all the solution in a single go, we have to go to select and left mouse click in this select option. Here we have to select all the solutions. After selecting all the solution, we have to define the axis values of the phase diagram. To select that, we have to go to this gray region and click left mouse click on this. Here the variable dialog box opens. In variables, we select what we want to vary. So in this case, we'll vary the gaseous partial pressure of oxygen. So we'll put 1 in this activity region. So we have to decrease the composition variance to 2 and then click on next. So we will set our temperature as our x-axis. So we have to go to this drop-down menu and select temperature as x-axis, where we have to give the minimum and maximum temperature in centigrade. So we'll put 500 and 1000 degrees centigrade as minimum and maximum temperature for these calculations. Also, have to select the y-axis. In y-axis, we will change the partial pressure of oxygen. To select the species, we have to select oxygen. And then in y-axis, we have to select for which range of partial pressure you want to check. So we'll check from minus 40, 10 to the minus 40 atm to minus 20 atm as maximum. And then we have to select the composition of our material. So in this case, as I have shown, we have composition of 1% manganese and 1% silicon in the alloy, and the rest is iron. So we'll put manganese as constant, and here this is mass fraction, so we'll put 0.01. And for silicon, to change the value of silicon, we put 0 in manganese, put 1 in silicon. Now silicon composition will fix, and we put similarly 0.01. And then all the data is given, so we'll click on OK with left mouse click. So after all the data is given, then we'll click on calculate with left mouse click button. Before going to the phase diagram, we have to add another database, which is FT-Lite, for proper phase diagram calculation. So to add another database, we have to go to reactants window in data search, and we'll take FT-Lite database 2. After that, we'll press calculate. By selecting all the solutions for FT-Lite, FT-Oxide, FS-Steel, and factor-PS, we get this phase diagram, which is calculated by FACSAGE. So in order to check which area corresponds to which phase, we can left mouse click on each area. It will tell us what are the phases. So therefore, we can get that at what partial pressure of oxygen and what temperature, which phases are stable, and what kind of oxide phases will form. Next, we will learn how to draw primary oxide formation diagram using FACSAGE software. Primary oxide formation diagram requires the temperature and the partial pressure of oxygen, and this partial pressure of oxygen is directly corresponds to the dew point temperature of the furnace. Therefore, if we know the annealing temperature and the dew point, then we can predict what will be the primary phase formed at the primary oxide phase formed at the surface of the steel during annealing. Thus, this gives us a map of what kind of phases to expect if we have a specific alloy composition and for a specific annealing temperature and partial pressure of oxygen. In this problem, we'll use iron manganese silicon alloy, and the annealing temperature will take 800 degrees centigrade, and the partial pressure of oxygen will take 10 to the power minus 28 atm. So in order to draw the primary oxide formation diagram, we have to first open Faxage figure module. To open Faxage phase diagram, we have to go and click on this phase diagram option with left mouse button. So the phase diagram dialog box opens. Then we have to first select the databases. So to select databases, we'll go to data search and left mouse click on it, and then we'll select all the required databases. So we'll take FactPS, FT Oxide, FS Steel, and FT Light, same as shown in the previous section of this video. And then after taking all the required databases, we'll click on OK with left mouse button. Then we'll add all our alloys, and that means the elements which is required for this alloys. So we need iron, manganese, silicon, and oxygen. Then we'll click on next. Here we'll select all the possible product species. First we'll select all the pure solid products. So select that. We'll go to this white box and left mouse click on it, and then after clicking on that, we have to select all the solution phases. To select all the solution phases at once, we have to go to select option and left mouse click on it and select all solutions. After selecting all the solutions, we have to input all the variable values. So to input that, we have to go to this gray area and left mouse click on it. This variable dialog box opens, and here we'll fix the composition of the gas. That means we have to fix the partial pressure of oxygen. So we put 1 in there, and then we'll vary the composition of manganese and silicon. So in the variable we put 2 and then click on next. Now in this case the temperature will be constant, so we'll keep it as constant at 800 degrees centigrade, and then we have to input the value of the partial pressure of oxygen here. So here the partial pressure of oxygen is constant, so in the drop down menu we select constant, and then we input the value minus 28 in log scale. Then we have to vary our manganese concentration, which is in mass fraction here. So to vary manganese value, we'll put value 1 in this place, and then this is the minimum value. We'll start from 0 to 0.03 in the y-axis. Similarly for silicon, we vary from 0 to 0.3 and keep it at x-axis, and then after all the values of the variables are input, then we click on OK with left mouse button. So all the required information are given to draw the phase diagram. Now we go to calculate and click our left mouse button on this calculate option. So now as you can see, Faxage had drawn this phase diagram for us, where we have manganese weight fraction in the y-axis and silicon weight fraction in the x-axis, and we have different phases. So to check what phases are there in this areas, you have to go and left mouse button click on it. So from this diagram, as you can see, this is the boundary above which if we pick any concentration there of manganese and silicon, there will be oxide phases forming. So if we keep our initial composition in the left side of this boundary, then there will be no oxidation happening at 800 degrees centigrade with partial pressure of 10 to the minus 28 of oxygen. So this boundary is known as the boundary for oxide phases. So we can take out all the other lines and just use this boundary to give us the information that what alloy composition should we select to avoid any kind of oxidation on the surface. In order to take out all the other lines, we have to first go to the normal addition mode, this pen option, and click on that, and then we want to take out all these lines to get the boundary. So we go to this intersection and left mouse click on there and double click on that. So there it is shown all the values of the points in this line, and then at this value it is highlighted as this gray area. So we click on split from and then click left mouse click OK. So this line is splitted, so we have this line separated, so we can take it out. So just click on that line and this is highlighted, and press click delete button from your keyboard and that line is gone. Similarly, we will do for all the other lines to extract this boundary. So as you can see, I have eliminated all the other lines and just extracted the boundary for primary oxidation diagram. So at the right of this boundary there will be oxide phases if we take any composition, and then at the left side of the boundary there will be no oxidation at these conditions. So we'll just name it as PO2 equals to 10 to the power minus 28. Increase the size of the text and then click on it. So this is the boundary for primary oxidation at partial pressure of oxygen 10 to the minus 28. Similarly, we can draw for other partial pressures, partial pressure of oxygen, the boundaries, and if we draw all the boundaries, we get a nice diagram which shows us that at what partial pressure of oxygen, means at what dew point, at what annealing temperature of the furnace, we can avoid oxidation by taking which kind of composition of the alloying elements. Therefore, we save this diagram and then we'll draw similar diagrams for other partial pressure. So to save that, we have to go to File, left click on it, and then Save As, and we are going to save it in the desktop as n minus 28.fit, and then I'll make other diagrams and I'll show how to superimpose all these boundaries in a single diagram. So here I have extracted the boundary for partial pressure of oxygen 10 to the minus 27, as you can see, and now I'll superimpose the similar boundary for 10 to the minus 28 partial pressure of oxygen, so the which I made before. So to do that, we have to go to this superimposed figure option and left mouse click on it, and from this we have to go to desktop, and as I have saved it, click on it and click, and it also shows. So we have to take this one, open, and see we have all these boundaries for different partial pressures. So this is a nice diagram to figure out at what partial pressure which composition to take, which should be the left of these boundaries, in order to avoid surface oxidation, primary oxidation, at a specific atmospheric condition of the annealing furnace. Another nice thing what we can do using this primary oxide formation diagram is to get the idea of secondary oxides. So if we trace this oxide phases at different partial pressures and then superimpose the this diagrams for different partial pressures, then we can get this kind of diagrams where for a specific temperature, by plotting all the for different partial pressure of oxygen, we can divide the primary oxidation diagram into regions of oxides. So what this diagram gives us is that, so if we have a specific composition of alloy, so then what first, by putting the composition value on this primary oxidation diagram, we can get what will be the primary oxide phase which is formed in our alloy. So if we take the composition A here, which have 1.5 weight percentage of silicon and 0.5 weight percentage of manganese, then we see that our primary oxide will be SiO2. Similarly, if we take the composition B, which is 1.5 weight percentage of manganese, 1.5 weight percentage of silicon, we have primary oxide as MnSiO3. And similarly, the same thing for composition C is Mn2SiO4. Now, as the oxidation reaction progresses, then what happens is that after primary phase formations, we can get secondary oxide phases too, because as we start from this composition at the surface of our alloy, then primary phase forms. So as you can see for composition A, which is Mn 0.5 and silicon 1.5 weight percentage, we have primary oxide phase as silicon dioxide SiO2. Now, as due to silicon SiO2 formation, the silicon at the surface gets depleted, then the surface composition drops in silicon and drops until at this composition, what will happen is simultaneous precipitation of silicon dioxide and MnSiO3, because this is the phase boundary, and then this composition will follow the phase boundary where both SiO2 and MnSiO3 will form simultaneously, and there the MnSiO3 is the secondary oxides. Therefore, by drawing primary oxidation diagram in FACSage, first we can get an idea for what kind of composition we should take to avoid the oxidation of the surface at the annealing condition for our composition. And also, by drawing this kind of oxidation diagrams, we can also predict that what type of primary phases, oxide phases will form at the surface, and also uh, what will be the secondary oxide phase formation, and how will the surface concentration change along with the oxide formation. Similarly, you can see a oxide phase diagram for iron 0.002 percentage of weight percentage of carbon, manganese SI steel. So here we varied the silicon and manganese weight percentages and fixed the carbon concentration and the annealing temperature, which is 800 degrees centigrade. And for different compositions, we can get what will be our primary and what will be our secondary oxides.